Number one, FRQ. Now this FRQ pretty much sums up all of Unit 8. Okay, we have the area between two curves, which is this first one. We have the area, or so the volume using revolution. It's a volume of revolution. And we have a volume using cross sections. Now, actually, when we learn this in Unit 8, we go this guy first, then this guy, and this one's last. All right, now this one is actually, I think, the hardest part, okay? So let's go through this step by step. First, we're just gonna talk about the area between two curves. Now, the area between these two curves, we have one curve right here and then one curve right here, is broken up into two sections. We have M and N, okay? Now, because there's two different sections, we have to be aware that the top function changes for each section. So for our M section, G is our top function. That's this curve right here. All right. And the reason why that's important is because when you find the area underneath the curve, like you integrate this dude right here, what you're going to get is if I go from this lower bound to this upper bound, all right, that's x1 and this is x2, our lower bound and upper bound. You're going to get this whole area, this whole thing, which is not actually what you want. You only want this area. So what you're going to have to do is you have to find this whole area, and then you have to subtract from that the area underneath the lower curve, which is right here. And once you subtract this one from the bigger one, you'll find the smaller area that you're actually looking for. Now, in order to do this, we're going to need the points of intersection right here and here. This one right here is obviously 0. This would be another x right here, and this right here we'll call this x2. All right, we have our lower boundary and upper boundary for this area, and then we have our lower boundary and upper boundary for this area. Okay, so just going to reference our formula sheet really fast. The area between two curves takes the upper function and lower function, subtracts them inside the integrand when your function is defined by x's. Okay, so we have our lower boundary, our upper boundary, those are x's, this is a dx. We do have other scenarios where our curves are not defined with x's, they're defined with y's, in which case you're choosing y values for your lower boundary and upper boundary. It would look like this, like if we were looking for this one right here, this area, our lower boundary would be here, and then our upper boundary would be here for this curve, whatever this curve right here, that would be f, but we have to change this so that it is written in terms of y's instead of x's. So that means you would take this, you would solve for each of the x's so that you have y's inside the function instead of x's. Okay, that would be your lower boundary, upper boundary, and then for this section right here, this would be your lower boundary, that would be your upper boundary. But that's for if your curves are defined with y's instead of x's. You would do right function minus left function. Okay, it's the same idea. Upper function minus lower function gives you the greater area minus the slower area. Now, how do you know which one's the upper, which one's the lower? Sometimes you don't have a graphing calculator or a picture that tells you. And if you don't know, that just means you're going to get a negative area. And if you get a negative area, just make it positive and your answer is correct. Another thing to be careful about, now this one shows us a picture. If a question ever says, find the area between G and F from 0 to whatever this number is, I think this is 0.89. If it says that and you don't have this cool, awesome picture, what you have to do is you have to make sure that the function doesn't intersect between 0 and the other, the ending part between the two functions. Okay, so needless to say, it is easier to do these functions when you have a picture. All right, so I first want to use Desmos because now we're allowed to use Desmos on the AP Calculus exam. When I put my functions in, I put them in exactly as I see them, okay? That way you can use f of x and g of x when you're doing the integrals like this, so you don't have to keep retyping out these functions, because if you do that, there's a good chance you're going to make a mistake. All right, so if I zoom in, I can make my picture kind of look like the one that is given to me in the problem. And then with Desmos, man, I love Desmos. You could just tap the point of intersection and you can see your x value, which is 0.227. That's why you see it right here. So for our first area, that's this one right here, it's 0 to 0.227. That's this part right here. Now our upper function is g, so we're going to go g minus f. our lower function, which is why you see that. I cannot combine these two because they have different upper and lower bounds. I did combine two integrals right here. Instead of going 0 to 0.227 of g of x, or dx, minus the smaller area, 0 to 0.227 f dx. Okay, instead of writing it like this, I wrote it like this because they have the same lower and upper bounds. It's kind of a quicker way to do it. All right, and this is what it would look like. I'm going to go int for integral, and then I'll be able to type in 0, right arrow, 0.227, and then inside the integrand in Desmos is really picky about this. You must put parentheses around your integrand. So I'm going to say f, and make sure you put your of x. Man, Desmos is so picky when he, oh, it's not f, dang it. It's supposed to be g. So g, and then we have f, close the integrand, and then I would put dx to get my answer. Now that's not all. I also want to add the area of n. So I'm going to do the same thing, but then I would have to tap this spot right here to find the other point of intersection. So here we go. It would look like this, plus int, and then we have 0.227, and then 0.89, and then my integrand, we have f of x minus g of x, close that parenthesis, and then we have dx. Boom shakalaka, you got your answer. Just make sure you put the of x part. That's what I wasn't doing earlier when I was getting ready for this video, and it kept messing up. I was typing in exactly this, but Desmos likes you to put the of x part. I mean, maybe if I took away the of x part in here where I defined f, I could just use f, but I guess you guys can play with that if you want to. All right, so if you guys have a graphing calculator, you're going to want to go to your function window. On the Texas Instrument, it kind of looks like this app. I would just press y equals, which is the top left button, and then I would put in my functions. Here's the part where a lot of students mess up. You see where my cursor is? That negative is not a minus sign. It is a negative sign. Only Texas Instruments does this. For the most part, I believe most Casios, they allow you to use the minus sign for the negative, but not Texas Instrument. The negative sign is down here by the point, and I can't, it's not highlighting, but it's over by the decimal point, okay? Double check. Right after you type in your functions, make sure you type them in correctly. I'm sorry, correctly, because if you do, make sure that you type it in correctly. You don't just have to use the y sub 1 for the f function for the rest of your problem, and you never have to worry about typing it in wrong again. All right, so this is how you do it on the graphing calculator. I'm going to press second quit. I could look at the graph if I want to. Oh, actually, you do have to look at the graph because we want to find the point of intersection. So let me show you guys how to do that. First, I'm going to change my window. I'm going to put my x min to be kind of the same as what is on my graph. So I have a negative 0.5, and then I see a 1 for my x max. And then for my y min, let's go down, clear. Y min, that looks like a 0.2. My y max, let's say that's a 1.3. And let's see what it looks like. Yay, it looks just like it. Okay, so that first point of intersection is already highlighted on my graph, but your graph probably doesn't have it highlighted. What you do is you press second trace. That would be calc, okay? Second calc. It's the trace button. Then you see the intersect option, which is 5, and my calculator does something slightly different than yours. Mine says what is your left bound and what is your right bound. What your calculator probably says is which curve or which function, or it says first curve, and then you have to select it by pressing enter, and then I'll say second curve, select it by pressing enter, and then you'll get a point on one of the graphs. You can jump to the different graph by going up or down, but you want to use the left or right arrows to drag that point closer and closer to the point of intersection, and then you press enter. For my calculator is saying, what is your left bound? And so I press enter, and then what is my right bound? I put the right side on the other side of the point of intersection. I press enter, and then it finds it for me. There's my point of intersection, is 0.227. All right, now I do actually have my other point of intersection, so I don't have to find it with this graphing calculator because I already did it with Desmos. But I want to show you guys how to find the integrals using the Texas Instrument. So second quit. All right, I'm going to show you guys the long way to find y-vars, and then I'm going to show you guys the short way. First, let's press math, and then we're going to press 9 for our integrals. If you guys have a newer graphing calculator, you'll have math print, which will look something like mine. Or if you don't, you have an older version, and you'll have to look it up online. I can explain it, but it will be hard for me to do it because I won't have a visual. But if you come to me in person, I can explain it to you, so no problem. All right, so I'm going to press 0, right arrow, 0.227, right arrow. And then I'm going to put my g function is y sub 2. So I'm going to put y sub 2 in there. So here's one way to do it. You press vars, because that's where you find all your variables. And then you go to y vars, so using my right arrow, and then select function. And then you have all your y vars right there. I need the y2, so I press a 2, and then I got my y2. Then I'm going to say minus. The other way to do it is you press alpha and then trace. Not everybody's calculator like mine says y vars right above trace, but it'll still work. Just press alpha trace. I need y1, so I'm going to use my arrow to select y1 and then press enter. All right, that one's done. Now let's add to that the other integral. So we're going to say 9 again, and then 0.227, and then 0.89. Here we're going to go alpha y var. I need y1, and I'm going to subtract from that alpha y2. And then I press enter once I'm done. Oh, it says invalid variable. Oh, this happened to me before. What is it? I think it's because I either have extra... Oh, man, I just deleted the whole thing. All right, there. Look, it worked right there. Let's see. Can I delete? Let's see. Delete. All right, let's just see if that one works. Yeah, that one works. Okay, so not sure why my app is being dumb, but... yeah, then it works. Okay, I don't get it. But anyways, that's how you use the Texas Instrument to find your answer. Remember, top curve minus bottom curve if you have functions that are defined by x, which is what these ones are. They're functions of x. Next, we're going to find the volume of a solid that is formed by revolving around a horizontal line. We like the horizontal lines because that means we get to use functions of x instead of functions of y. So we have a horizontal axis. Okay, so one we're going to say is right here. All right, and I just want to show you guys what it would look like if we revolved m. Now, just the top function. Let's not concern ourselves with the bottom function. So if I found the area underneath this all the way down to the axis revolution, this is the solid we're going to get. It's going to take this area and it's going to make this big loop. It's not a bad circle, okay, and it's going to become a solid, all right? Now, I don't want this ginormous solid. I only want the solid that is formed when I revolve this part around that axis. And so we get this ginormous volume from the top one, and then we get a little smaller one when I revolve just the bottom curve around this axis of symmetry. It would be like that. Okay, now if I want to find the area of this one circle, we all know that an area of a circle is pi r squared. Well, how do I find r? Our r is going to be found by the curve, which in this case is f, and I'm going to subtract that from my axis of symmetry, which is -1. Okay, like let's say, for example, this curve right here at this point is 0.5. So 0.5. And if I subtract the axis of revolution, I would get 1.5. All right. And that would be my radius for just this one circle. Now we have a bunch of radiuses from all these points on this curve from our lower boundary and our upper boundary. So instead of saying 0.5, I'm going to say f. And we're going to say f of x minus -1, which is really just adding 1, which gives you the radius of the circles that are formed when you revolve the f around the axis of revolution. Whew, that's a mouthful. So instead of pi r squared, we're going to go pi f plus 1 squared. Remember, this is the radius right here. All right, I'm not dividing it by r. That's the radius. And then what we're going to do is we're going to integrate this so that we can add all of those circles that that solid has to find the volume. Now this will give me the smaller volume. To get the bigger volume, I'm going to have to go pi, and then I'm going to go g minus the axis of revolution and square that, which is actually just plus 1. Okay, so that's going to be my bigger solid. Now, because the lower boundary and the upper boundary will be the same for each of these, we can combine these two integrals to look like this. Okay, the pi right now is on the outside because he's a scalar. I could take this pi out and I could take this pi out and then integrate. When I take a pi out of each of these, it's just one pi sitting on the outside. Okay, so next you would plug this into your graphing calculator. Don't forget when you plug it into to Desmos, you're gonna have to use extra parentheses because it wants you to parenthesize the integrand. And that's how you're gonna find the volume of the solid that revolves m around the axis y equals -1. Okay, now this is known as the washer method, but what it is just the disk method twice. You're doing the disk method for G, then you're doing the disk method for F, and you're subtracting them. If you check out your formula sheet, it says this. Here's your disk method, okay? Outer function minus the axis, that will give you your radius. You square that, multiply it by pi, that's gonna be your area function for each of those disks that make up the solid, okay? Now, if you have more than one curve, you're gonna have an outer function and an inner function. In this one, this was our outer function because when I revolved it around this axis of this axis of revolution, that was the bigger solid. That made the bigger solid. When I revolved this one around the axis of revolution, it made the smaller solid. So you have r squared, minus r squared for the inner one, and then you do your integral with it. All right. Okay. Now for these two volumes, I didn't rewrite it for the y's, but I did do that with the volume using cross sections, and this is worth talking about because we're going to do this next. Now for these two, the area was just pi r squared. Those were the cross sections. For these cross sections, they could be any shape. The hard part here is defining these area functions. This one's with respect to x, this one's with respect to y, because you have to use only what you know, and that's the distance between the two curves. So for our last problem on this, we don't have to solve it, we just have to set it up, which I think is kind of weird for this problem because since it's a calculator problem, normally it would just have you solve it. Okay, but we're just going to talk about how to set it up. Now, remember, it's just x1, x2, that's your lower and upper bound. You have your area function defined by x, dx. All right, this is all we're doing, okay? No problem. It is the harder one to do. So when I'm looking at my area right here, we have squares, all right? Here's a square right here. If I go over here to this x value, I would have a bigger square. It would be a little bit taller because this line right here would be longer. Okay, so depending on where you're at, you're gonna have a different size square. So we have to be able to write an area function that's defined by x because these squares are perpendicular to the x-axis. All right, now if I want to find the length of this line, I just would have to do top minus bottom. Hey, we've seen that concept before. So it's going to be g minus f. That's going to give me the length of that side. Now that side is the bottom side of my square. Now, cool thing about squares is that you just need this one side and then you square it. That's how you find the area of it. So we go, the area function is going to equal g minus f, and then we square it. G minus f is the length of this side. Yay, that's it. Okay, so now we have our area function. Now you just have to integrate this foo, and you got it. You're done. Don't forget your lower and upper bound though. Okay, so that's what we have down here. We have g minus f, and we're squaring it, And it just so happens that this one's also square, but this one's those are circles. This one's a square. That's why there's no pi. And we have my lower and my upper bound. And that's how you would set it up.